In this lesson we're using simultaneous equations and we're going to try to solve them. So a simultaneous equation is looking at, say, two of these y equals mx plus c linear equations that we're used to seeing by now, two different ones, and what we're trying to find is the point at which, if we graphed them on the x and y axis, they would actually intersect, they would meet. Now if we looked at, say, parallel lines with the same gradient that would go on for and ever and never meet, they don't have a point of intersection, but some of them actually do, and that's what we're trying to find. This one wouldn't have a solution, these ones would. Okay, so that's what we're trying to achieve. So I've got two equations here, they're both in the form of y equals mx plus c, they're already done, and we're saying that y1 is going to equal this and y2 is going to equal that. Now at the point at which they intersect, we are looking at the same coordinates, so the same x and y coordinates. So that means we could assume that at the point they meet, y is the same as y. Y would equal 1. Oh, sorry, y1 equals y2. So if we know that, we can say that at the point, at the intersection, if y1 equals y2, then we can substitute and say that this whole chunk of the y is equal to this. So we can rearrange that. 3x plus 2 is equal to y, and we know that that is going to equal the same as whatever 7x minus 8 equals. So we can actually do that and balance them out. Now it's just a matter of rearranging, and we're used to rearranging our formula. So firstly, let's take this, subtract 8 and put it over here. So we are adding 8 on, which means we'd be adding 10. And we'd be left with 7x on that side. Let's then take this 3x and put it over the other side. So we're left with 10 here equals, we're going to add 3x on the other side, so we're going to have 10x, and then we've got 10 equals 10x. We know if we divide 10 by 10, we're going to get our value for x, which is 1. So now, if we've got that, we can actually do a check. Therefore, if y equals negative 3x plus 2, at x equals 1, y is going to look, we're going to substitute in for x, so negative 3 times our 1 plus 2, so negative 3 plus 2, which will give us negative 1. So therefore, the point of intersection, we've already got a coordinate now, is at x equals 1 and y equals negative 1. Now a way we could check is to substitute it back into our other formula. We've already done this one, we've checked this one, now we can check this second one. So we could say at x equals 1, y2 equals 7x minus 8. We're getting a bit squishy here, I'm very sorry. And we would then say, alright, 7x, 7 times 1 is 7, take 8, and that's actually going to give us negative 1. So that's fine as well. Okay, let's try and use our space more efficiently on this side. Same idea though, but this time there's a difference in that here we had y equals and y equals, so we could immediately make them balance out, but we can't this time because this one is in the form of y equals mx plus c, but this one, its subject is still a number. So what we can say is, alright, well if y equals x plus 3 at the point of intersection, then let's just substitute this whole chunk in instead of y up here. Okay, because we wouldn't assume, just like we did over here, that at that point of intersection the y are going to be the same. So let's say all of this is the y in this one. So we can, let's call this one 1 and let's call this one 2. We substitute 2 into 1. Right? So we're going to substitute the whole equation of 2 into the whole equation of 1. So this time, every time we see a y, we're going to replace it with an x plus 3. So now we have 2x minus 3 times x plus 3 instead of y, because we're changing it, but everything else stays the same. So we're going to have to do some quick expansion. So 2x minus, we're going to have 3x, and then take 3 times 3, which is 9, will give us this. Right, now we have to rearrange to find x. So 2x take 3x is going to be negative 1x, take 9, so we can simplify that. And now let's move this part over to there, so we're left with 1x is equal to, we're going to add 9 over there, which means we are negative 8 plus 9 equals 1. and therefore x is going to equal to 1 divided, negative 1, which is equal to negative 1, right? So now, if our x value, when we're trying to find that point of intersection, if the x value where that happens is 1, then y, back up here to number 2, y is going to equal x plus 3, because we set up here, well, that's what it's going to be. So now we have an x value, we can say, all right, that's 1 plus 3. Oh, sorry, this should be negative 1. X equals negative 1, so negative 1 plus 3, and that's going to equal 2. Right, so our point of intersection is x equals negative 1 and the y equals 2. Let's do that check again. Let's say our other formula, or y equals, doesn't have in that form, we have it in 2x minus 3y equals negative 8. At x equals negative 1, we should get an answer of y equals 2, so let's do that. We can say, we actually can check that because we have a y and an x. Let's say, all right, 2 times our negative 1 minus our 3 times our 2 value should equal this, and 2 times negative 1 is negative 2, and then we take off 6, and that actually does equal negative 8. So we've found the right point. So these two graphs intersect or cross over at negative 1, 2, whereas it's a bit easier to do these ones because we can see that our y's are equal. So two very similar but slightly different skills there. Substituting in one of our formulas into the other to replace the y, given that we know what y equals, or balancing out. If we know that y and y should be the same, we can say this whole chunk equals this whole chunk.